All right, welcome back. And so this is our what is it? The third part of the session for today. It's a pleasure to introduce our speaker, Mauricio Romo from Tsinghua University. I've known Mauricio for many years. I think we met in Sanya in a conference, and I was so impressed with his knowledge about gauge linear Sigma model. So I've been following him ever since then to, make him teach me a lot about gauge linear Sigma model. So he's gonna tell us about A-branes. A-branes.
Not about systems. So I'm also a physicist, not only at heart, also in practice. So hopefully this talk can be something where you can learn something as a mathematician and as a physicist. So the title of the talk is Networks and BPS Counting. So I call it A-brane view. Okay, so it's not only a sample, as I mentioned, it's something kind of a bit of a recent topic, a little bit of underdevelopment. There are a lot of development topics, so some things and some are not clear even in a physics way. So it's a bit of a set of crazy ideas that come together and give you some concrete conjectures. So it's based on a series of papers. So papers, we just write papers, not write all the academic papers with my two collaborators, Sivasic Banerjee and Romo. Kind of between 19 and this year. So the talk essentially will be divided in two parts. So one part will be about something called 5D BPS states, or 5D BPS invariants, maybe I should call it. And its relation we will see with some mathematical invariants that are more familiar to you, and the concept of exponential networks. And then the second part is time, which unfortunately is the kind of the most, where some of the more recent conjectures lie, but I don't know if I will have time to this part. But in the second part, I will talk about interpretation, of these invariants, as I will put it in quotation, counting of special Lagrangians. Okay. We will see where that comes from. So now first, let me start then with the first part, so with the physics setting. So the physics setting, there are some things that actually Kumrum talk about here. So the physics setting is on M theory, and again, if you don't know the physics, it's okay. But for the ones that know, since I know several people in the audience know quite some physics, some maybe more than me, I will mention it. So the context is M theory on the following space. So it's 11-dimensional. This X will be taken for all this talk, will be a toric Calabi-Yau threefold. Toric Calabi-Yau threefold for physicists, and for the effect of this talk, we will always having in our heads the Calabi-Yau threefold has some symplectic quotient. Something like this. So this is some moment map, this is some level set, you can have many, and this some torus. So this just so you have this image in your head. I will do some examples when time comes. But what we are doing, if we put M theory on this kind of background, we can read 5-dimensional. There is a very natural 5-dimensional field theory, T for theory, that's determined by the topology and the geometry depends how much you want to know about it, of this Calabi-Yau. So this is the theory, the 5D theory that lives in this piece of the space. Because this is non-compact, so in order to kind of isolate this theory, you need to use something called geometric engineering that I won't mention. So I can mention. And yeah, and this S1 is some very special circle that called the M theory circle that in a second in our story. But so what is the thing? What are the BPS invariants? So what the goal, one of the goals, or the main goal maybe, is to count bound states of BPS or supersymmetric BPS membranes M5, M2, and M5 branes, which are some 6-dimensional and 3-dimensional objects with the following topology. So because the BPS, part of what makes them BPS is they have a special topology. It cannot be just any 6- and 3-dimensional submanifold of this space. So these branes are wrapping things like the S1, this S1 times C2. I will say well C2 and M5, for example, will wrap like this S1 and some R2. So all these are inside the R4 process 1 times C4. And what are C2 and C4? So CA are holomorphic A cycles in X. So once you have these things, this kind of object realized from the point of view of the 5-dimensional theory, this looks like some particle around the circle. You just ignore this part, and this looks like a surface defect, a 3-dimensional defect. So these invariants are you can denote it like omega 5D and omega 5D, and omega 5D are depending on several things. So they are depending on the momentum around this circle of this particle. They also depend on the class of this cycle and on the class of this cycle. By reduction to string theory, by reduction to type 2A, meaning you just reduce, you make the circle really small, but it's a very delicate process. But the reason I'm telling you this is because these invariants that are omega 5D, or I will denote them simply omega in the following, are equivalent to Donaldson-Thomas invariants, where this number here will be the class of the point. So if you know Donaldson-Thomas theory, is labeled, the invariants are labeled by a class in cohomology. So the class will be this. I will denote here this because of the usual notation with like a sum. So in principle here there could be D6, but in this case the D6 is you can add it. It is infinite volume. But so in the case of the theory, the way we approach this problem is you cannot see it directly. So we are going to consider Donaldson-Thomas invariant. Maybe you can call them of rank 0. I don't know. That's the standard way of calling them. But they are labeled. They are numbers. So these are some numbers, and they are labeled by this class. And they have a mathematical definition.
So, you don't want to take multiple of C2 and C4?
Because it's here because the class doesn't have to be like a primitive.
Oh, okay.
It can be
so it's not a fixed.
Yeah, exactly. Just to make for the notation to be more compact. yeah, evidently you want to have things like that, and examples of these numbers. So in case you want also to relate it with something more familiar, we have computed, for example, if you have k, here we can have just k, so none of this. So this would be the same as Donaldson-Thomas invariance of k. We call the points the 0 branes and this, so the 2 branes and this the 4 branes. It's just basic notation, so 4, 2, and 0. So this is like k, the 0 branes, so k points, and the numbers you get is the Euler characteristic of x with a negative sign here, and it doesn't depend on k. And another is one example, and another example. This, of course, also defined appropriately because kx is non-compact. And here also you can have things like this. You can have k of the this, and you can have, for example, some C2, some class that I can call beta, and none of this, like just this. So this will be the Donaldson-Thomas invariance with k d 0 and some class beta here. And these ones are very special because this one equivalent, I will write it like this, so they're not precisely equal, but equivalent to Gromov-Witten invariance of genus G and class beta. This equivalence is MN of B. Yeah, Mauricio Romo o Bandari old times, not so old. And the equivalence is kind of it's not, as I said, it's not that they are equal. It's not that you match k with g or something like that. There is some generating functions that you have to match. Okay, but so that's to relate this invariance to something more natural. So now let me go to the question on how you actually compute. So in order to compute those numbers, of course, you have many techniques. You can say, well, you are not computing anything new. If you know those Donaldson-Thomas invariants, there are several ways to compute it. But the idea of all this thing I'm going to say is that you want to compute it. The idea is to compute it using only some kind of a model data. It will came up in a second. Or in other words, the idea is to come up with some kind of Fukaya category definition of the Donaldson-Thomas invariant. So not using this this holomorphic cycle, but something else. Yes.
Yeah, so after I'm vibrant, do you want to write R1 plus S1 or do you want to write R2 plus 1? I think this does not have that.
This one? Oh, I'm really sorry. This guy. Oh, yeah. Six.
What is the motivation for the counting problem? Do you want to expand some
Oh, well, I mean, it's not one motivation is they will allow you to make some mathematical predictions. Because this number is well defined mathematically. This one not quite. Yeah, in this case it's only non-compact Calabi-Yau. So yeah, they are associated to black hole microstate, but we I'm not that expert on black holes. From the physics, so okay, let me talk about, so the physics motivation is just, this also is like some counting of some class of BPS states. Not all the possible BPS state on this 5D. It's only a BPS state that looks like a particle or like a surface effect with the atom.
But what do you learn if it describes some black hole microstates?
It describes this like, so I don't understand the math papers on Donaldson-Thomas. So the only way I can understand those numbers is if I compute this in a very complicated way. I mean, I don't understand the features class. I need to come up with some way, right? Yeah, the motivations of the pure mathematical, right? So So now, but now let me make a connection with something else that you may know. The motivation, the something else is that there is the way to compute this is we use ideas from EMN. So what's EMN? This is periodo. Some works of periodo Moore and Knightsky. So they, which are the spectral network. Let me tell you the idea, because it's of course it's a huge series of papers that ended up on the spectral networks, originally pioneered actually by Clem, Meyer, Baffa, and Warner. But the idea is to use a defect M5 rank. And this part, it will some mysterious things will appear, but this I need to say something at least about that, about this, in order to explain some things that will come up. So this US space, so what you take is some Lagrangians here. They call it the Lagrangian defect. Okay, just in case I can. So this is a Lagrangian. And here is S1. Now it's a small processor, so it's an M5. So why I do this? So you do this, and this one by geometric engineering. I have a 3D theory, and people that know about AGT will not be surprised by that. I have a 3D theory that's determined by this Lagrangian defect. So one way to compute these 5D states is then compute something called 3D 5D BPS invariants, which are some invariants that lives on this theory. And these are related. This will give you information. These are related by a very, very intricate way, which I hope we can describe. These are related to the desired omega phi d. So what are these? They're called 3D 5D because whatever is the theory on 3D, cannot forget that comes from a defect on this theory. Okay, so this part is it's very physical. It may not, for some people here, may not make much sense, but I really have to say that in order to explain what's going on, or at least it doesn't look that I'm too crazy. Okay. Yes. So very good. So now, what comes? How you compute this 3D 5D? How you compute this, and how you eventually relate to this. So so the steps are the following. So the 3D 5D states. So I give you a map of what I'm going to do now. The 3D 5D states are equivalent to some solitons, and this I'm going to be concrete in a second. Solitons on T3D. And once I have this, then you analyze a flat connection on the space of solitons. This has a name, and this is called a non-Abelianization map. And this is what is going to give me the 5D thing. So I hope at least we're going to get to explain that relation, because it's a very non-trivial relation. So these are just some words. Now let's put more equations on these words. So let's start here, okay? So there is a bunch of, there are two important things on this 3D theory that I will call two things that I will call X and Y, which we can think them belonging to C star, and for later reference, I will denote C star sub X and C star sub Y, because I will write this C star in several places. So there are two coordinates in C star that from the point of view of the 3D theory have very distinguished interpretation. This is some 3D chiral field, so it's like a field, or it's like the web of a field, chiral field on the 3D theory. And this X is coupling constant. Is on coupling constant. So X and Y satisfy an algebraic relation. An algebraic relation, which I will denote f of x y equals to 0. And this defines a curve in this C star. A curve that I will call C. So there is some algebraic relation, and this algebraic relation depends on your choice of L depth. So the relation actually, this curve sigma, if L depth is appropriate, if it's chosen, coincides with the mirror curve of X. Let me give you one example. So for instance, you can take X equal C3. So there is a toric diagram for this that have appeared in many talks. That's the toric diagram. I can consider this L depth a toric, something that's called a toric Lagrangian, or also a Ganagi buffer branes, which usually are denoted like this. So there are branes that have topology. They have some topology R2 plus X1, and whose position is determined by this diagram. Then the moduli space of the formation of this of the A-brane on this Lagrangian correspond to this curve with some circle above it. So for example, in this case, f xy will be given by something like this. So something like 1 plus x plus y plus x, y, something of this sort. This is one example. Okay. So I don't know if there's any notes so far, any questions? Maybe many, but I just.
Can you determine that relation to the fiction directly, or
No, this relation. Not from the, yeah, you can read it from the Newton polygon.
oh,
Yeah, and maybe if you know what it is, the y square look a little bit strange, is because I'm using another framing, not the standard frame. Okay. But topologically, that curve is the same like 1 plus x plus y, which will be the natural. So yeah, this part may be a bit very confusing, but the important thing, this is one of the important pieces to take out, that these are there's two very distinguished coordinates on this three-dimensional theory, and they are related by something like which is, you can imagine, has some superpotential. Okay, so now what you are going to do, as I mentioned here, is to count solitons, or maybe I would like it to call BPS solitons on this 3D theory. So what are the BPS solitons on this theory? So the BPS solitons will be of the following way. So I have, first of all, I have to look here is my C star X. So this is kind of my space of couplings, right? So call the curve this Fx equal to 0 look from, if I write the space of coupling here, the curve will be like some, right? There will be some branch cover. I can think sigma over C star X is some branch cover. So the coordinates here are y of x, comma x, the coordinate here is obviously x. So this y of x actually there are different sheets, right? That can come together at some particular point. So I label the sheets like I and j, etc. So what I'm going to compute here is if I have a point x, for example, above this is the coupling, so I fix my coupling here. A soliton, a 3D, 5D soliton, so here I need some color, will be a point joining the two pre-images of x. Like this is one pre-image of x, and this is the other pre-image of x. So this is y, I can call it yi of x, and this is yj of x. Soliton have that form. So they can be like that, and there is what makes them BPS soliton is that, so this soliton, for example, y of x of t, if t is like the parameter along this soliton, is BPS, is equivalent to say that this curve, this orange curve, we can call it gamma. Gamma is calibrated by the differential log of y dx or n. So there is a natural differential on this curve, which is the reduction of it comes from the differential in this space on the C star cross C star. And this curve that joins these 2 points must be calibrated by this differential. So the phase of this differential must remain constant along this curve. But the problem is this differential is not meromorphic, as you may imagine if you're familiar with spectral network, but it has a logarithmic singularity. It has a log of y that makes your life incredibly more complicated. That means this is a technicality, which is extremely important, but in order to save time, I'm just going to mention here, because for the pictures, it doesn't matter too much. But the technicality is because you want to do this calculation, you have to go one step further to the logarithmic cover. So the coordinates here will be y of x. I can write it explicitly like this. So this y, the logarithmic coordinate, and this n is the logarithmic cover. So I have a branch cover which is finite, and I can have an infinite cover about it. It has infinite number of sheets because it's the logarithmic cover. I just took the log. Okay, so calibrated by this differential means that the curve must satisfy a differential equation, which is the following. So y sub I, which would be the logarithmic, the log of the in this sheet, minus y sub j, something of this sort. So how to make it explicit, as here. Where theta is my calibration parameter. So it's a parameter that will, I mean, with parameter is BPS solidon. In physics, it has to do with what half of the supersymmetry this solidon preserves. So in the math picture, you can think of this theta has some stability parameter for those lines inside sigma or sigma t. So written like this, the only difference with this picture is just not to make it too messy, is that now it goes between I, comma, and 1. And here it goes to the sheet j, comma, and 2. And this is n2 and 1 and eventually a convention. But this is the difference. So it's just you will have infinite more sheets. So in the case of spectral network, you don't have this for horrible n. That's the main difference, and what makes your life more complicated. So depending on how you choose this theta, so now I don't know if I will be able to do this drawing. So you can have like branch points here. So here a branch point that joins, for example, sheets ij. I'm going to skip the n label. So here some branch points, and let's say here some branch point that joins where the sheets I and another sheet k comes together, and above this, potentially, if I have another random point here, potentially there can be, right, some solidon like this. For example, also I can have above these points, I can also have something. You see that? Something like that. But k and j doesn't intersect. So when you project in this space, how this solidon will look like? Well, it will look like something started from the branch point and going to x, right? It's just the projection. So here, for example, sorry for my picture, but these things will look like this, for example. So at the end of the day, if you keep drawing all this projection of these solidons at a fixed theta, you will get something that looks like this. So you will have like your branch points where a j or another branch point where maybe jk comes together, and you will have like, you can have things going like this. You can have more than one, etc., etc. And maybe at the intersections, you can also have this. Your homework to see how that comes from this picture is easy, but if I try to draw it, it will be a disaster. But you can see that one coming like this, going like this, going out. So there can be something like that. So you at fixed theta, you will have like a collection of these solid. Okay, a horrible picture for generic theta. But for generic theta, you will have a horrible picture, and this picture is this thing is what is called the exponential network. Spectral networks pretty much look the same. The difference, as I said, is that this singularity will be meromorphic instead of logarithmic, and therefore you will have a picture that looks slightly less horrible. Okay, so and as you move theta, of course, these networks will change in some way. The main difference between logarithmic and spectral is that in spectral networks, usually when you have intersection, you can have one coming out. In the logarithmic picture, you can have an infinite number coming out. But again, that's super different. That is really a technicality, and we are not doing the computations explicit here. But so these are the networks, and the networks this is the sense in which the networks are parameterizing the moduli space of 3D, 5D BPS state, this solid. This is the sense in which the networks reflect this solid. So they're usually drawn in this way and projected here. Of course, each path has you can give a direction, and you can also give a label. So now, still, I haven't told you how you can compute any number out of these networks. So the network themselves contains a lot of information, contains more information than probably what you want. However, there exists special thetas, special angles called critical, that I will call critical angles. Here are. So at theta critical, what happened is that some portion of the network is coming together. So let's say this is one example. So omega of theta critical looks like this. So these two come together. For example, I wrote some directions. It's not very important. So if you go to, let's say, theta slightly above theta critical, your network will look like this. So only at certain angles, there are some paths, all these paths have dimension. There is a way to give them a direction. Only at certain angles, this path will degenerate. So this is what you will call a degenerate network. And they contain some very funny things, because if you erase everything that's not degenerate, you are only left with this guy. So there is a sub-network, which is the degenerate path. For example, in my little picture here, the degenerate path is just this line going between the two branch points. So let's say it's a branch point, another branch point. This undirected path, if you want, that I can call gamma critical, are very interesting, because gamma critical, I shouldn't have. Gamma critical leads to a closed cycle in.
So, Mauricio, can I, so the differential equation you raised.
Yeah.
So I should think of the right-hand side, E theta, I theta, as sort of the inhomogeneous term for this differential equation. It's a problem.
It's more like in the terms of like Calabi-Yau, it will be the equivalent to you take like your omega 3,0 form.
Yeah.
When you restrict to the Lagrangian,
Yeah,
you make it like the volume form with the is a special Lagrangian condition.
so what is the solution of the equation, tell me?
The solution of the equation are these lines.
So
And that means it along these lines, the top holomorphic form, we are talking about that curve, right?
Yeah.
So the top holomorphic form is just 1,0. Right? So the 1,0 is the one I wrote, which is this one. So what means is this.
But the solution is the function you call x tau, right?
That's right.
So this is the function that's supposed to be function on the upper half plane.
It will be a function in the curve, because y is related to x via this equation.
Yes.
So here I have y of x. Implicitly, I can solve for y of x.
So how is tau related to?
Oh, tau is just a parameter. Tau, tau is just a parameter along the curve. You can take it just any real. You can take it from 0 to infinity or from minus infinity to infinity.
So the solution are these curve
This orange.
in the
orange
network.
Yeah, yeah.
And you're supposed to trace them in order to count the BPS.
I'm going to say now what happened. So what is this network? What is doing? I mean, okay. Sorry, that maybe wasn't too clear. Is so at this point, it's parameterizing all. At this point, let's say in the system, it's parameterizing all the possible solitons that can appear at this coupling. Remember that it has the definition of a coupling. And then I just move the coupling through all the plane. So at most points, like let's say this one, for a fixed theta, for a fixed condition, stability condition, there will be just no solution at all. So it's only a very special point, this one, for a fixed theta, where I can find some solitons going around.
Okay, so theta is the stability.
It's a stability parameter.
Yeah,
It is
slow.
It's a slow. Yeah, it's slow. Yes, it's slow. That's correct. So I can move it as I wish, and I'm just saying there's some thetas where this kind of phenomenon will happen, where the network will degenerate. So, and when it degenerates, I can isolate the part of the network that degenerates and say, okay, this gamma C, this degenerate actually lift to a closed cycle in sigma. You can see why. So in this case, for example, to degenerate, this branch point must be of type ij. This must be of the same type. Otherwise, this cannot happen. It's not like this. So then when you lift to sigma, this obviously the lift of this to sigma will look like, right? Like between the old branch. Okay, so
the special values depend on your curve, right?
absolutely. And actually, the curve I give on the example doesn't have moduli itself. Like if you do like you look at P1, for example, you have another parameter, but that usually keep fixed. But yes, depends absolutely on the curve. The shape and everything of the network is completely dependent on this f of x, f comma x comma y. So yeah, okay. So I think I just only have time to state how you get the omega 5d. Unfortunately, we cannot talk about the A-branes. I think so, right? Because I found until 470, right? Is that true? Yeah, okay. A few. I can state.
435.
Yeah, I can state this result. I mean, this result. No, I mean, what I mean is I cannot tell you the A-brane story, but that will take like another 45 minutes. So let me tell you how you get the omega 5 database. Okay, so what I promise is that there is a flat connection over this moduli space of BPS of 3D5D BPS state. So what happens? So now non-abelianization map. And this is going to play a role, okay? So there exists some this is non-abelian bundle in there this you just have to believe that there exists some non-abelian bundle over C star, so it's a very simple spacious punctured which locally it splits into line bundles L sub I, comma n for each sheet. So this is the over all the sheets. In case I put the n explicitly, so these are line bundles over sigma tilde. Actually, we are completely we want to be correct in that state. So locally they split like that. One can see that this happened, but this is true. I mean, this can be made true. Actually, no. So there is a map here, which I will call psi sub w theta, because it's a map that's determined by the. So let me give you one picture, and with that, hopefully that explains what happened with this map. So what this means, so this bundle comes with a flat connection. So NA for non-abelian, and these collections of L's also come with a flat connection that I will call abelian. So I can use that picture, for example. So let's say, remember this was the C star X plane. So if you take path, if you take a path here that I call P, you take a path and you take the holonomy along P of the non-abelian connection. I will omit the flat part. That's equal to some combination of some numbers that belongs to Z of holonomy, a combination of holonomies around gamma of the abelian connection. And this gamma are paths inside sigma tilde. So it's not so hard to imagine, because what you have is like a path here, like you have a path here, and this gamma are just, this is I and J, these gamma are just the preimages. You can have gamma I, gamma J. These gammas are just the preimages of P into the sigma or sigma tilde. So these numbers here, these are integer numbers, and they happen to be non-trivial when P crosses one of these net. And what they are doing, these numbers, this mu gamma theta, are the, we can say these are precisely the 3D 5D solid. Okay, this number, and they essentially are counting, for example, that the path that's crossed here essentially counting the number of solutions of the differential equation at this coupling. So the number of paths that goes at this coupling.
So this would actually agree with the DT invariant?
Not yet. Now we come to DT. One more formula needs DT, sorry. The problem is it's a bit of okay, so in general, those mu are nearly impossible to compute. You can compute them by consistency because the deltas, these guys are flat. So if you take this path, the holonomy around this path, and let's say around this path, have to be the same, as long as you don't encircle the function. But this is just the star x, so it's really simple. So using flatness of this, you can kind of bootstrap this mu, but that's not what you really want. What you really want is to know the following. So mu, gamma theta, why I put theta? Because these guys are integer, but they depend on theta. They jump as we vary theta if we cross a theta critical. When you cross the theta critical, there is a jump on this integer. So the claim is that this jump can be implemented as a cluster transformation in the last formula of the talk, so don't be nervous. So let's call these guys just to write the formula. I will call it gamma x sub gamma. Yeah, sorry to use x so many times. As a cluster transformation, x sub gamma to x sub gamma times plus minus, but depends again on the situation, gamma c omega gamma c, this is an integer, and this is also another integer because this is pairing, it's some intersection pairing. Define also carefully because these paths are open in principle, except gamma c, gamma critical, I erase it, but gamma critical is closed. So there is a transformation of this sort that implements the jump on this mu. So the claim is that this omega gamma c is omega by the of gamma c. But in order to match the gamma c to a class of holomorphic cycles, for that I need the second part of the talk. So I will leave that in a mystery for you. So I stop here. Thank you for your attention.